Welcome back to the channel, everyone. We're going to do part 2 today, so this video will follow on from the introduction. We're going to begin by just looking at how we would relate two complex numbers to each other. And once we've done that, we're going to look at how we might add, subtract, and multiply complex numbers together. And in the next video, we're going to look at division. It takes a bit longer. There's a bit more explaining in the division. The addition, subtraction, multiplication, pretty straightforward. So let's get straight into it. First of all, I want to talk about what happens when two complex numbers are equal to each other, because we approach this in a very different way to what we would when we regularly solve algebraic problems. So our natural instinct, I would say, when we see an equal sign with some x's and y's, our natural instinct is to start moving things over to one side to maybe get it to say x equals or something like that. We're going to approach these very different and complex numbers, and this is an ongoing skill. It's actually a skill that pops up quite a lot in exams in different formats. But one thing we need to be very, very clear about is when we have two complex numbers with an equal sign, we do not start rearranging. Instead, if two complex numbers are equal, the real must equal the real, and the imaginary must equal the imaginary. This is a very, very, very important concept in complex numbers. Instead of rearranging, you're just trying to make sure the real part is equal to the real part and the imaginary part is equal to the imaginary part. So if we look at our first example, pretty straightforward. I want to determine what the x and the y are in this situation. We have got x plus 3i is equal to 2 minus iy. You can see on this side the x has no I with it. It's just x, which means it's the real part. And if I look over to the other side, the 2 is the real part. There is no I. For these two complex numbers to be equal, the real part must equal the real part, and therefore I can conclude straight away that x must be 2. 2 for the real, 2 for the real, they have to be the same. In a similar way, I can start to look at the imaginary part now. So positive 3i, that's my imaginary part, needs to be the same as minus 2i. Now this seems like, we've got some sort of contradiction. I've got plus 3 and minus iy. Now instead of, when I write the equation out, I'm not going to actually use the I. So all I need is 3, the imaginary part, to be equal to minus y, the imaginary part. I need the two imaginary parts, but I don't include the I in this calculation, just the number with them. 3 is with the I, the minus y is with the I, and now I can just multiply both sides by -1 or divide both sides by -1. Either way, it's going to tell me that y needs to be equal to minus 3. And there I have found my solution to the first problem. X is 2, y is minus 3. If I put that in, you'll see I get 2 plus 3i. X was 2, we just said. And I'll get 2 minus minus 3. A minus minus becomes a plus, and now we've got the exact same complex number on both sides. Let's look at it. It can get a tiny bit more confusing, but let's have a look at this one. All right, so when I look at the real, we have x. When I look at the real, I have y. I'm not being told too much information there other than the fact that x is equal to y. That's my real part. Making the real parts equal in that equation, I end up with x is equal to y. The real is equal to the real. Now when I look at the imaginary part, I start to get some information. When I look at the imaginary, I have y. And when I look at the imaginary, I have 3. And so that tells me that y is equal to 3. And when I look above, x is equal to y. And so x is also equal to 3. A little bit of a cryptic message there, but we can put that in. X is 3, we get 3. Y is 3, we get 3i. And y is 3 plus 3i. You can see that they are the exact same complex number if I let x and y both be 3. Lastly, even harder now, we might even end up with some sort of simultaneous equation with this one. We've got a little bit more work to do, but the exact same approach. When I think about the real, when I just look at the real parts of these two complex numbers with the equal sign in the middle, I want the real part on this side to equal the real part on this side. We can see the real part is anything without I. It's this x plus y. When I look at the real part on the other side, it's just 1. So I have an equation, x plus y equals 1. That's great. Let's look at the imaginary part. So I've got 2 with my I. So 2 is equal to x minus y, the things that have I on this side. And now I have a simultaneous equation. There's different ways that you might want to solve it. I'm going to solve it using substitution. So I'm going to rewrite this equation so that it says x is equal to 1 minus y. And now I'm going to substitute that wherever I see x in this equation. So this is going to come in down here. I end up with 2 is equal to x. Well, x is 1 minus y, and there's minus another y. So I've changed that x to be 1 minus y. I still have this minus y. That is now 2 is equal to 1 minus 2y. I'm going to subtract the 1 over here and get a 1 is equal to negative 2y. I'm going to divide by negative 2 and get y is equal to negative a half. Or 1 divided by negative 2. Great. I can then use my first equation, which was x is equal to 1 minus y, and put these two together to end up with x equaling 1 minus a half, which is 1 plus a half, which we're going to write as 3 over 2 or 1.5. And those are my x's and y's. All right, so this is an important skill, very, very important skill. When you see an equal sign with a complex number, don't start rearranging things. You make the real equal the real, the imaginary equal the imaginary. Great. Now let's look at addition and subtraction. Now these skills are not too hard. We should breeze through these. When we're using addition and subtraction of complex numbers, it would be ideal if when we add a complex number, we get another complex number. We're going to think in terms of our junior school algebra, we're going to be adding like terms. The best way to do it is we're just going to look at some examples. It'll be very, very clear. U equals 5 plus 2i. V is equal to negative 2 plus I. W is equal to negative 3i. Now, I said in the first video we use Z to denote a random complex number. When we actually have like a one that we're going to be using, quite often they use the late letters in the alphabet. U, V, W, all that stuff. Z would be when we don't really know what it is. Z equals A plus BI, we don't know what it is. When we actually have a particular one like this, we use U, V's, and W's a lot. You'll notice this all through textbooks and all through exams. So if I want to first of all do U plus V, I'm literally writing 5 plus 2i, that's my U, and I'm plussing V, minus 2 plus I. So that's my U, that's my V. I'm adding them and I'm thinking like terms. I'm going to add my whole numbers, my 5 and my minus 2, or my real parts, and we end up with positive 3. I'm going to add my imaginary ones, 2i. We can imagine just an I as a 1i, so that's going to be 3i, and that would be our final answer to that problem. Adding my real parts, adding my imaginary parts, just like terms. Okay. Similarly, we can do U plus V plus W. Just going to add a whole lot of stuff. 5 plus 2i, that's my U. Minus 2 plus I, that's my V. And then minus 3i. So we already know what that first stuff is. We just did it. It's 3 plus 3i. And then I'm minusing 3i. And the i's are going to cancel. My final result will be a positive 3. Finished, done, happy, love it. Subtraction, exactly the same. We have to be very, very, very careful when we subtract because we are subtracting the whole complex number. So a common mistake that I see a lot, so this one is W, which is minus 3i, and I'm minusing U. Now a very, very, very common mistake I see is they say minus 5 plus 2i. Now this is bad. This is not good. The reason being is that this minus is for all of you. Currently, all I've done is minus the 5. I need to minus all of you. To make sure I'm doing that, I put a bracket around it, or you think very carefully that you minus both parts of that. So this now becomes minus 3i, minus 5, minus 2i, and now we can get to our final answer, which in this case, I've got minus 3i, minus 2i is going to be minus 5i, and minus 5. Probably should have put the real part at the front, minus 5i. That's how we're used to seeing it. But that's fine. You can notice all of these are still complex numbers. I could still plot them on our little graph from yesterday. 3 plus 3i, I'd go across 3 up 3i. Just the 3 is a purely real number, so that would just be on the real axis, and minus 5, I could plot that. Last one, real quick, it's just u take away 2i. So it's 5 plus 2i, take away 2i, we get the solid answer of 5, and we know how to add and subtract complex numbers. Very quickly, we're going to look at multiplying. Again, it's pretty straightforward. Similar stuff. Multiplying, to do this, we're going to think similar to expanding brackets. There is one other thing that we need to remember way back from the first video. One of the earlier things we looked at was when we were defining complex numbers, we said that I squared was minus 1. And we're going to need to use this fact in this problem, in using this skill. So we had I was the square root of negative 1, and we had I squared equals negative 1. This pops up a bit. So same UVW, let's look at how we could multiply them instead of add or subtract. UV, so U is 5 plus 2i. I'm going to put it in a bracket and times it by V, which is minus 2 plus I. Expanding this bracket, just like algebra, I multiply the front two things. I've got minus 10, 5 times I is, we're just going to call that 5i. 2i times by minus 2 is going to be minus 4i, and 2i times by I is going to be 2i squared. All right, so we can tidy this up a little bit. Minus 10 plus I plus 2i squared. Now what we don't like is that this actually doesn't now look like a complex number. Complex numbers were just the real part and the imaginary part, and I have this random imaginary part squared here, which we don't like. Currently I don't even know how to graph this on the graph. And then we look up here and we say, oh look, I squared is negative 1. So I can put that directly here. So now the answer will be negative 10 plus I plus 2, and I squared is negative 1. So that's times by negative 1, which makes that part negative 2. My final answer now is I can merge my 10 and my minus 2 together to be minus 12 plus I, and we have another complex number. Multiplying 2 together, and we still ended up with one that we could plot. It's negative 12 in the real and 1 in the imaginary. Look at one more quick example. Hopefully you've got it by now. If you want to pause it and try this, see how you go. So this is going to be negative 3i, which is my W, times by V, which is minus 2 plus I. Just putting this information here down here. The V is the negative, the W is negative 3i. The V is minus 2 plus I. We're going to expand this bracket. Just one thing at the front, so it's going to multiply to both of those things in the bracket. Minus 3i times minus 2 is going to become positive 6i. And minus 3i times by I is going to be minus 3i squared. Soon, when you practice this a bit, you'll become very familiar. Straight away, I squared is negative 1. And you can just imagine that negative 3 is being multiplied by negative 1. And so this is 6i plus 3. And that's because this is, as I said, negative 3 times by negative 1, which is a positive 3. And we now know how to add, subtract, and multiply complex numbers to end up with another complex number that I can then plot if I needed to. Awesome. So that's great. In our next video, we are going to look at how to divide. There's a little bit more needed to divide, but hopefully this video was useful to you. If it is useful, feel free to like and subscribe. Any support is appreciated, and we'll catch you guys later.